Kubernetes can look like a long list of objects, pods, deployments, services, ingresses, config maps, volumes, roles, and more. That list is useful, but it hides the one idea that makes the architecture coherent. Kubernetes is a distributed control system. You describe the state you want. The API records that declaration. Controllers observe the actual state, compare it with the declaration, and take bounded actions to reduce the difference. Nodes then run the workload. The system repeats this loop because machines fail, traffic changes, images change, people make mistakes, and capacity moves. In this CipherVibe deep dive, we will build one end-to-end mental model instead of memorizing isolated commands. A product team wants to run an online checkout service. Their change begins as a declared workload. It travels through authentication, authorization, admission, storage, scheduling, image retrieval, runtime creation, networking, health checks, routing, telemetry, autoscaling, and recovery. Every layer gets its own diagram. By the end, you should be able to trace a request from a GET change to a customer response, and trace an incident backward from a failed response to the control that owns it. Kubernetes is not a magic computer, and it is not the same thing as containers. It is an orchestration platform that coordinates containerized workloads across machines. It also does not supply every production capability by itself. Networking, storage, ingress, observability, identity integration, backup, and policy often involve carefully selected add-ons or cloud services. The core question throughout this video is simple: what is the desired state, which component owns the next reconciliation step, and how do we verify the result? Kubernetes is API-driven. A resource is a structured object with identity, desired state, observed state, and metadata. The identity usually includes a kind, a name, and often a namespace. Labels create a flexible way to group objects. An object spec is the desired contract, perhaps 3 replicas using a particular image, with requests for CPU and memory, a port, and a readiness check. Its status is written by the system to report what has actually been observed, which generation is current, which conditions are true, and what has not converged. That distinction explains a great deal of Kubernetes behavior. When you request 3 replicas, you do not make 3 operating system processes appear directly. You create a durable desired state record. A deployment controller creates or updates a replica set. The replica set controller creates pods. The scheduler assigns unbound pods to nodes. Kubelets on those nodes create containers. Each component updates status as it progresses. The API object graph is therefore not just configuration, it is the shared, inspectable ledger of intent and evidence. Metadata matters because automation depends on it. Labels connect services to pods, policies to namespaces, cost allocation to workloads, and dashboards to ownership. Owner references establish which controller may clean up dependent objects. Finalizers can delay deletion until a controller completes a required external action, such as cleaning up infrastructure. A practical rule is to treat the spec as a promise made by a team and status as evidence collected by the platform. If the two disagree, do not jump straight to the node. Follow the ownership chain and conditions until you find the controller waiting for something. The KubeApp Observer is the central interface to the Kubernetes control plane. Clients include administrators using command line tools, continuous delivery systems, controllers, schedulers, kubelets, and add-ons. They do not normally modify shared cluster state by talking directly to each other. They send API requests. The API server authenticates the caller, authorizes the requested action, runs admission controls for writes, validates the object, persists accepted state, and exposes watch streams so other components can react. This is why the API server deserves special care. It is not an application load balancer. It is the control plane boundary. Authentication establishes an identity, perhaps a human using an external identity provider, an X.509 client certificate, or a workload using a service account token. Authorization evaluates whether that identity may perform a verb on a resource in a scope. Admission may mutate defaults or reject an object that violates policy. The request then reaches validation and storage. Read requests have their own authorization and audit considerations, while create, update, delete, and connect style requests receive the richer admission path. The API is also an event source. Controllers use watches rather than scanning blindly every second. A controller sees that a deployment changed, queues work, compares desired and observed state, and updates its dependents. The scheduler watches for unscheduled pods. Kubelets watch pods assigned to their own node. This watch-driven design is efficient, but it means API availability and latency influence the entire cluster's ability to converge. Existing pods can often continue serving traffic during a control plane disruption, yet new work, rescheduling, status updates, and configuration changes may be delayed. The control plane decides. It does not directly execute your application's request path. ECT is the consistent, highly available key-value store used for Kubernetes API data. It is the memory behind the declarative model. When the API server accepts a deployment, a service, a secret, a node record, a lease, or a controller status update, that state is stored through the API. Controllers then see changes by watching the API at particular resource versions. The important operational message is that ECT is not a casual application database. It contains the state required for the control plane to understand what the cluster is supposed to be. Consistency and quorum matter. A typical highly available control plane uses multiple ECT members so the system can tolerate a member failure while maintaining a majority that can agree on changes. If the cluster loses quorum, it should not keep accepting conflicting writes just to appear available. The safe response is to protect the durable state, recover carefully, and avoid improvising destructive repairs during an outage. The exact topology depends on your distribution or managed service, but the architectural principle does not. Safeguard the system of record before worrying about a dashboard. Secrets deserve a specific note. Kubernetes objects called secrets are API objects, not automatically an end-to-end secret management strategy. Teams should understand how their environment protects data at rest, whether encryption at rest is configured for sensitive resources, who can read or create secrets through the API, how external secret sources are synchronized, and how backups are protected. An ECT backup can be essential for recovery and extremely sensitive at the same time. Document the backup cadence, test restoration in a safe environment, secure access to the backup location, and keep restore procedures separate from the pressure of an actual incident. The strongest control plane is one whose state and recovery path are both rehearsed. A controller is a control loop built around a resource or relationship. It watches relevant state, calculates the difference between what exists and what is desired, takes an action, and checks again. That loop is called reconciliation. The deployment controller is an easy example. If the desired spec says 3 replicas at a new image version, it creates or scales replica sets according to rollout rules. The replica set controller then works to keep the selected number of pods present. If a pod disappears, the controller creates a replacement. No central script needs to remember every outage, the desired count remains in the API and the controller keeps correcting drift. Controllers are intentionally idempotent. The same reconciliation may run more than once because a watch event repeats, a process restarts, a network call times out, or an update conflicts. A robust controller can see that a dependent object already exists and move on safely. This is one reason Kubernetes feels different from an imperative shell workflow. You describe the outcome, then let controllers retry toward it. It also explains why you should avoid changing controller-managed children by hand. If you manually delete a pod under a replica set, the deletion may be immediately corrected. If you edit a field the controller owns, a later reconciliation may restore the desired value. Not every failure is a controller failure. A controller may create a pod correctly while the scheduler cannot place it. It may request a load balancer correctly while the cloud integration is waiting for quota or permissions. It may issue a deletion while a finalizer intentionally pauses completion. Read conditions, events, owner references, and observe generations before assuming the word controller means an opaque black box. In a healthy cluster, reconciliation is visible, scoped, auditable automation. A node is the execution environment for pods. It may be a virtual machine, a physical server, or, in some environments, a specialized compute instance. The kubelet is the Kubernetes agent that runs on each node. It watches for pods assigned to that node, works with the container runtime to make them real, prepares volumes and network interfaces through configured plugins, runs health probes, and reports status back to the API server. The runtime performs the container lifecycle work, pulling images, creating containers, starting them, and reporting their local state through the container runtime interface. Kubeproxy is another common node component. It programs or coordinates service traffic handling, though some networking implementations provide an integrated alternative. Nodes also host the CNI components that create pod networking and the CSI components that attach or mount storage when needed. Node-level logging agents, metrics exporters, security sensors, and device plugins are usually additional workload components rather than a hidden part of every Kubernetes installation. This is one reason node design needs capacity planning. Applications are not the only consumers of node CPU, memory, disk, ports, and network bandwidth. Nodes themselves are API objects with conditions and capacity. The control plane tracks whether a node is ready, unreachable, under pressure, or unavailable for scheduling. A node failure has two stages in the architecture. First, the control plane decides the node is unhealthy after missed signals and grace periods. Second, workload controllers create replacements elsewhere when the workload design permits it. That transition is not instant, and it cannot protect an application that has only one replica, one zone, or a stateful dependency with no tested recovery path. Kubernetes can help replace work. It cannot invent capacity, duplicate data safely by default, or turn one machine into high availability. A pod is Kubernetes' smallest deployable unit. It is not merely a synonym for a container. A pod groups one or more containers that are meant to run together. They share a network namespace, which means they usually share one pod IP address and can communicate over localhost. They can also share declared volumes. Each container still has its own process and image, but the pod establishes the local execution envelope, startup order, restart behavior, resource accounting, service identity, and a common lifecycle. Most application pods have one primary container. Additional containers should solve a clear local problem, not become a substitute for service boundaries. An init container performs preparation before application containers begin, for example, waiting for a dependency under an approved pattern, rendering local configuration, or establishing a file system condition. A sidecar runs alongside the main application to provide a tightly coupled function such as a proxy or local helper. The design question is whether the components need the same network identity, same scaling unit, and same failure domain. If they do not, separate pods and services may be clearer. Pods are intentionally ephemeral. Do not treat a pod name, a pod IP address, or local writable file system data as a durable application identity. A controller can create a replacement with a different name and IP. Services, DNS, persistent volumes, external databases, and durable object storage solve different continuity problems. The pod abstraction helps make containerized work movable, but it also makes lifecycle design visible. Define resource requests, limits where appropriate, probes, security context, termination behavior, and volume needs as part of the pod template. A pod that starts is not necessarily ready. A pod that is ready is not necessarily reachable. A pod that terminates may still be draining a request. Those distinctions become essential as the architecture grows. For a stateless web application such as our Checkout API, a deployment is usually the right workload controller. A deployment describes the desired pod template and rollout strategy. It manages one or more replica sets. A replica set maintains a chosen number of matching pods. This layering may initially feel indirect, but it gives Kubernetes a way to preserve old and new revisions during a controlled rollout. The deployment can scale a new replica set up, wait for readiness, scale an old replica set down, and retain enough history to support a rollback decision. The word stateless does not mean the application has no state. It means that any healthy replica can generally handle an equivalent request because durable state lives in a separate system or a deliberately managed data layer. A shopping cart service might keep session data in a database or a cache. A web frontend might be recreated at any time because the canonical assets come from an image or external content store. If two replicas are interchangeable, Kubernetes can place, restart, and scale them without needing a fixed identity for each one. Design the template carefully. Labels on the pod template should match the selectors expected by the replica set and services. A selector is an ownership contract, so changing it casually can create unexpected overlap or orphaned resources. Include readiness probes so a newly started container does not receive customer traffic until it can serve the intended operation. Use a deployment strategy that matches the application's compatibility requirements. A rolling update is common, but it needs enough headroom to run old and new replicas temporarily. Some releases need a more deliberate blue-green or canary pattern implemented through a delivery controller, gateway routing, or service selection. Kubernetes manages declared replicas. Your architecture must decide what safe to replace means. Kubernetes provides multiple workload controllers because not every process is a replaceable web replica. A stateful set manages pods that need a stable identity. Each replica has an ordinal identity and can be associated with its own persistent storage. This can suit a distributed database or a clustered system that needs an ordered membership model, but it does not eliminate the need to understand the application's replication, backup, quorum, and recovery semantics. Persistent storage makes data survive a pod replacement. It does not guarantee the database is correct after a multi-zone outage. A daemon set ensures that eligible nodes run a copy of a pod. Common examples include a node-level log agent, network component, storage component, or hardware helper. A daemon set is about node coverage, not a customer-facing replica count. When the node fleet grows, the controller creates another pod. When a node becomes ineligible, the controller may remove or avoid one. Resource requests and scheduling rules still matter because these pods share the node with applications. A job represents work that runs to completion, such as a bounded migration, report generation, or batch processing task. A cron job creates jobs on a schedule. Think carefully about retry behavior, concurrency, idempotency, late starts, time zones, and the effect of a duplicate execution. Kubernetes can retry a failed pod, but only the application understands whether running the underlying business action twice is safe. These controller choices are architecture choices. The shortcut "put every container in a deployment" hides important assumptions about identity, completion, and data. Choose the controller based on what must remain stable, what must run everywhere, what must finish once, and what must repeat according to a defined schedule. The scheduler watches for pods that have not been bound to a node. It does not start their containers. Its job is to select a suitable node. In broad terms, it filters out infeasible nodes and scores the remaining candidates. A node may be infeasible because it lacks allocatable resources for the pod's requests, does not satisfy a required node selector or affinity rule, has a taint the pod does not tolerate, cannot access the required storage, violates topology constraints, or conflicts with other scheduling rules. If no node is feasible, the pod stays pending and Kubernetes reports why through status and events. After filtering, the scheduler scores feasible nodes. Scoring can consider distribution, resource balance, affinity preferences, data locality, and configured scheduling policies. The scheduler then writes the binding through the API. The chosen node's kubelet notices the assignment and takes over the local execution work. This separation is important. A scheduling decision is a control plane commitment, a running container is a node plane result. If a pod is bound but not running, inspect kubelet, image, volume, and runtime conditions. If it is not bound, inspect scheduling constraints and capacity. Placement rules are powerful, but each rule is a constraint on resilience and utilization. Pod anti-affinity can keep replicas apart so one node failure does not remove all of them, but overly strict rules can make a small cluster impossible to schedule. Topology spread constraints can distribute work across zones or hosts. Taints repel general workloads from special nodes, tolerations allow particular pods to consider them. A toleration alone does not guarantee placement. Resource requests and limits establish a starting economic contract. The scheduler needs accurate requests to make credible placement decisions. Capacity planning begins in the pod spec, not in a surprising outage dashboard. CPU and memory requests tell the scheduler what a container needs as a baseline for placement. Limits define a ceiling for runtime enforcement where configured. They answer different questions. A request helps prevent the scheduler from packing more declared demand onto a node than its allocatable capacity can support. A limit helps prevent one workload from consuming unlimited runtime resources. Neither value should be copied from an example without measurement. Too low requests create an illusion of spare capacity and lead to contention. Too high requests strand capacity and make pods pending even when observed utilization is small. CPU is often compressible. A process may be throttled when it exceeds its available CPU. Memory pressure is different. When the node is under pressure, the operating system and kubelet may need to reclaim resources, and a container that exceeds its memory limit can be terminated. Kubernetes also uses quality of service concepts and pod priority to make decisions under pressure. These mechanisms are safeguards, not a substitute for correct application sizing or load testing. A service that needs a predictable latency budget should understand how CPU throttling, garbage collection, queues, and downstream dependencies behave under realistic load. Remember the system overhead. Nodes run kubelet, runtime, networking, storage, logging, metrics, and sometimes security agents. Pods may have init or sidecar containers. Empty dir volumes can consume ephemeral local storage. Image layers require disk. A workload may request CPU and memory but still fail because a node has insufficient ephemeral storage or a configured resource quota blocks the namespace. Teams should establish a feedback loop, define an initial profile, instrument actual usage, review saturation and throttling, adjust safely, and keep enough capacity for rollouts and failures. Resource specifications are not paperwork. They are the first input into scheduling, autoscaling, disruption behavior, and cost. Kubernetes defines a networking model rather than one universal packet implementation. Each pod gets its own unique cluster-wide IP address. Containers in the same pod share a network namespace and use localhost to reach one another. The pod network is expected to allow communication between pods across nodes without requiring each application to understand a special proxy or translation scheme. The implementation details come from the Container Network Interface, commonly called CNI, and from the infrastructure beneath it. Different environments implement that model using different routes, overlays, eBPF programs, virtual switches, cloud network interfaces, or combinations. The architecture lesson is to distinguish the Kubernetes contract from the provider mechanics. Your application should normally address another application through a service name, not hardcode a pod IP. Your operations team must still understand how pod sitters, node routes, DNS, load balancers, network policy enforcement, and egress behave in the selected environment. Network troubleshooting begins with the model and then narrows to the implementation. Network boundaries deserve explicit design. By default, depending on the CNI and policy configuration, broad pod-to-pod reachability may exist. Network policy objects express permitted traffic at the IP and port level, but the network implementation must enforce them for the policy to have effect. A policy API record that no data plane interprets is not a boundary. Build a diagram for each production namespace, which clients arrive from outside, which services may call which backends, which systems require egress, what DNS paths are necessary, and which telemetry endpoints are allowed. The goal is not to make every packet mysterious. The goal is to make legitimate paths clear enough that unintended ones can be denied and investigated. Pods are disposable, so callers need a stable way to find the current healthy backends. A service provides that abstraction. It identifies a logical set of endpoints, usually matching pods through labels, and exposes a stable virtual address or hostname. The control plane maintains endpoint slice objects that describe the current backends. A service proxy implementation programs the data plane so packets arriving for the service reach an appropriate endpoint. The implementation may use kubeproxy or an integrated mechanism from the networking layer. Clustered DNS is the usual discovery method. A DNS component watches services and exposes names that resolve inside the cluster. A pod in one namespace can reach a service in the same namespace by its short name, while callers in another namespace use a qualified name. The precise DNS suffix is cluster-specific, but the architecture is stable. Application code targets a logical service identity, while the control plane and network layer track ephemeral replicas. Do not use environment variable service discovery for a design that needs dynamic creation order. DNS is generally more flexible because a lookup can resolve after the caller starts. Readiness is the bridge between workload health and service traffic. A pod can be scheduled and running yet excluded from ready endpoints until its readiness condition succeeds. That prevents a process that has only opened a port, or is still warming a cache, from receiving customer traffic. If traffic is missing, trace the chain in order. Does the service selector match the expected labels? Do current endpoint slices contain the intended pods? Are the endpoints ready? Does the caller resolve the expected name? Does the service data plane have a permitted route? A service is not a load balancer in the abstract. It is an API object, control plane endpoint membership, DNS identity, and data plane routing behavior working together. A service gives a workload a stable identity inside the cluster. External traffic needs an additional edge design. A service of type load balancer can request a provider-supported load balancer for a particular service. Node port exposes a port on nodes, usually as a building block rather than the final public architecture. For protocol-aware HTTP and HTTPS routing, teams commonly use Gateway API or an existing ingress implementation. The Kubernetes project recommends Gateway API for new capabilities. Ingress remains stable but its API is frozen. The terms matter. An ingress or gateway resource describes routing intent, but a controller or implementation must fulfill it. That implementation may create or configure a cloud load balancer, a proxy fleet, a physical edge router, certificates, health checks, and internal routes. The resource is not the packet processor by itself. This is a common source of confusion when a route exists in the API but no controller is watching its class. Permissions prevent infrastructure creation, a certificate has not become ready, or the target service has no healthy endpoints. For our checkout application, the customer request follows a deliberate path: domain name to public edge, TLS termination or pass-through according to policy, host and path routing, internal service, selected ready pod, then downstream internal services. At each boundary, declare what must be enforced: certificate lifecycle, client authentication where required, rate limits, request size, timeout, header policy, web application protections, observability, and egress rules. Do not expose every service simply because it has a port. The architecture should distinguish internet-facing entry points, private partner paths, internal application calls, administrative interfaces, and health endpoints. A well-designed edge makes the public surface smaller and the routing evidence clearer. A container file system is usually ephemeral. When a pod is replaced, local writable data may disappear with it. Persistent storage uses a separate object model. A persistent volume claim, or PVC, is a request for storage with a capacity, access mode, and often a storage class. A persistent volume, or PV, represents storage that has been provisioned inbound. A container storage interface driver, called CSI, connects Kubernetes to the storage system that can create, attach, mount, resize, snapshot, or otherwise manage the backing resource according to the environment. This separation is powerful because a pod can be replaced while its claim remains. It also makes the real design decisions visible. Which access mode does the workload need? Can the backing storage be mounted in more than one place? Is the storage block, file, or object-based? Is it zone local? What happens when the scheduler selects a node in a different failure domain? How are expansion, encryption, snapshots, backup, retention, and deletion handled? Kubernetes may coordinate some of these actions. It does not erase the characteristics of the underlying storage platform. Stateful workloads need a recovery story before they need a YAML story.
A stateful set can give each replica its own persistent claim and stable name.
But operators still need application-consistent backups, tested restores, replication topology, upgrade plans, capacity thresholds, and a clear understanding of data durability. A volume snapshot may be useful but is not automatically a transaction-consistent database backup. A PVC bound successfully does not prove a workload is resilient to a regional outage. Keep the data lifecycle diagram beside the pod diagram: request, provision, attach or mount, use, snapshot, retain or delete, restore, and decommission. This is how a persistent claim becomes a recoverable service. A healthy delivery model separates application code from environment-specific configuration. The container image should contain the versioned application artifact. Kubernetes can provide non-sensitive configuration through config maps and sensitive data through secrets, either directly or through a designed integration with an external secret manager. A pod can receive these values as environment variables or mounted files. The choice affects rotation behavior, process startup, auditability, and the risk of accidental exposure in diagnostic output. The word secret should encourage caution, not false confidence. Secrets are Kubernetes API objects subject to API authorization, storage protection, backups, audit policy, and the permissions of the workload that mounts them. A user or service account that can read a secret may be able to obtain its value. A pod that receives a credential has responsibility for keeping it out of logs, error messages, crash dumps, and debug endpoints. Instead of giving every workload broad access to a shared namespace, scope configuration, and identity to the smallest practical unit. Keep sensitive values out of container images, source control, command histories, unprotected shell environments, and informal copies. For the checkout service, distinguish 4 input categories. First, static non-sensitive behavior such as a feature flag default or service URL. Second, sensitive connection material. Third, workload identity used to obtain short-lived authority. Fourth, deployment metadata such as version, owner, environment, and trace configuration. Each has a different lifecycle. A code change may require a new image. A configuration change may require a rollout or dynamic reload. A credential rotation may require an overlap window and revocation plan. A service identity should be auditable and least privileged. If these categories are mixed into one opaque environment blob, deployment becomes fragile and incident response becomes unsafe. Configuration architecture is application architecture. Kubernetes access control begins at the API server. Authentication establishes who or what is calling. Authorization determines whether that identity may perform a requested verb on a resource, usually within a namespace or sometimes cluster-wide. Role-based access control, known as RBASI, defines reusable permission rules in roles and cluster roles, then binds them to users, groups, or service accounts through role bindings and cluster role bindings. The goal is not to create one master token that makes operations easy. The goal is to make legitimate work possible with the smallest authority necessary. Namespace scope is an important boundary. Use a role binding where permissions should apply to one namespace. Reserve broad cluster role bindings for genuinely cluster-wide responsibilities that have been reviewed. Treat powerful verbs and resources with care. The ability to create workloads, read secrets, bind high-privilege roles, modify admission webhooks, create credential requests, or attach to a running pod can have consequences beyond a simple read or write. Kubernetes documentation emphasizes least privilege because broad access can create escalation paths even when no individual permission looks like cluster administrator. Workload identity deserves the same rigor. A pod can use a service account to call the Kubernetes API or to integrate with external workload identity mechanisms. Do not automatically mount an API credential into every pod if the workload does not need it. Do not reuse one service account across unrelated applications just because it is convenient. Give a payment worker, a metrics collector, and a deployment controller separate identities, separate bindings, and separate audit trails. When an API audit event appears, your team should be able to answer who made the call, which workload or human initiated it, what resource was accessed, what role allowed it, and whether the action matches the expected operational path.
Identity turns the API from an anonymous control channel into an accountable boundary. Authentication answers who is calling. Authorization answers whether that caller may request an action.
Admission answers whether the resulting object is acceptable for this cluster at this moment.
Admission controllers can modify eligible objects to add safe defaults or reject objects that violate policy.
They operate on create, update, delete, and certain connect style requests, not ordinary reads. A rejection at admission stops the request before the new desired state is persisted.
This makes admission the natural place for platform guardrails.
An organization may require resource requests, restrict privileged runtime settings, enforce approved registries, require labels that identify an owner, prevent public exposure in sensitive namespaces, or apply pod security standards. Validating admission policies and external policy engines can express different styles of rule. The governing principle is consistent: define a clear rule, test it against legitimate workloads, provide actionable rejection messages, audit exceptions, and avoid making production depend on an unavailable or unobserved policy path without an explicit availability decision.
Policies must be layered.
A workload can pass an image policy but still have unnecessary API permissions. It can pass a pod security check but still reach a sensitive database because network boundaries are missing. It can have a network policy but be exposed through a misconfigured public gateway. Avoid the false goal of one policy object that makes a cluster secure. Instead, build a pipeline of independent checks: identity, authorization, admission, runtime isolation, network controls, secret handling, image provenance, logging, and response.
The advantage of the API-based model is evidence.
You can show which object was requested, which policy evaluated it, which version of the rule applied, and why it was allowed or denied. Good guardrails make the secure path the normal path without hiding the architecture from application teams.
When a pod is bound to a node, the kubelet begins the local startup workflow.
It obtains the desired pod specification from the API, makes sure required images are available according to pull policy, prepares volume mounts, asks the network implementation to create the pod interface, establishes the sandbox, starts init containers, then starts application and sidecar containers.
Each stage can fail independently. An image pull may fail because the reference is wrong, the registry is unavailable, a credential is missing, a network path is blocked, or a policy rejects an unapproved source. A volume may wait for provisioning or attachment. A CNI call may fail. An init container may exit unsuccessfully. A container may start and then crash repeatedly. For secure software delivery, think of the image reference as an artifact identity, not a vague label. Tags can move. A digest identifies specific content.
Many organizations add policy and verification steps around registries, build provenance, vulnerability management, signing, and approved base images.
Kubernetes does not turn an image into trusted software simply because it starts.
The build system, registry controls, admission policy, runtime configuration, and observability all contribute to the assurance story.
The startup diagram also guides troubleshooting. If a pod is pending, the problem may be scheduling or provisioning. If it is container creating, inspect volumes, network, and image events.
If it is crash loop backoff, inspect container exit codes, logs, configuration, and dependencies.
If it is running but not ready, inspect the readiness condition and actual service behavior.
Avoid fixing symptoms by repeatedly deleting a pod.
Controllers may recreate it with the same flawed specification.
The desired state is still the source. Trace the status and events back to the object, dependency, or policy that is preventing convergence, then make a deliberate change through the management plane.
A container process existing is not enough evidence to send it production traffic.
Kubernetes gives distinct probe types for distinct questions. A startup probe protects a slow-starting application from premature liveness failure while it initializes. A liveness probe asks whether Kubernetes should restart a container that is stuck or unhealthy. A readiness probe asks whether the pod should be considered ready for service endpoints. These should not be treated as three copies of the same HTTP check. They represent different lifecycle decisions with different blast radius. Readiness is particularly important during rollouts and dependency disruptions.
A pod can remain running but temporarily report not ready, which removes it from normal service endpoint selection.
The application should decide readiness based on its ability to serve the user-facing contract, not merely whether a local port responds. At the same time, avoid defining readiness as a fragile dependency chain where any unrelated service outage makes every front-end disappear.
Model essential dependencies deliberately, use timeouts and fallbacks, and test the behavior under partial failure. Termination has a matching sequence.
When Kubernetes removes a pod, a controller, scale operation, or node event begins termination.
Endpoint propagation should stop sending new traffic. The process receives a termination signal and has a grace period to complete shutdown behavior. Applications should stop accepting new work, drain in-flight work according to their protocol, flush only safe state, and exit.
A pre-stop action may be appropriate in some designs, but it should be simple, bounded, and observable. Treat the grace period as a contract verified with load tests, not a number copied from a tutorial. Poor lifecycle design produces the familiar release problem where a rollout is technically successful but users see dropped requests. Health and shutdown are not operational decoration, they are part of the software interface Kubernetes uses to make changes safely. A deployment rollout is Kubernetes reconciling from one pod template revision to another. The deployment creates or updates a new replica set, gradually increases it according to the strategy, and scales down the old replica set while maintaining configured availability.
Readiness conditions are central. A new replica that starts but does not become ready cannot safely replace an old healthy one.
Settings such as maximum surge and maximum unavailable express how much temporary capacity and service reduction the system can tolerate during the transition.
This is not the same as proving that a release is good. Kubernetes can tell you that replicas became ready.
It cannot know whether the checkout calculation is correct, the database migration is backward compatible, a feature flag causes a business error, or a downstream API is returning subtle incorrect results. Mature delivery adds layers around the native rollout, automated tests before admission, image and dependency scanning, staged environments, feature flags, synthetic checks, metrics-based analysis, approval rules for high-impact changes, and a known rollback procedure. GitOps tools can make the desired state and its change history explicit, while progressive delivery controllers can add canary analysis and traffic weighting. Those are architecture additions, not excuses to ignore native deployment conditions.
Configuration changes need the same discipline as image changes. A pod does not necessarily reload mounted configuration or environment variables in the way an operator expects.
Decide whether a configuration update requires a restart, a rolling rollout, or application-level dynamic reload, and make that visible. For rollback, know whether returning to an old image is safe after a schema change or external side effect. The safest releases are designed for compatibility in both directions during the transition.
Kubernetes gives you a structured way to change replicas.
Your application and delivery process must define what change safety actually means.
Autoscaling is not one switch.
Horizontal pod autoscaling, usually called HPA, is an API resource and controller that adjusts the replica count of a scalable workload based on observed metrics. It may use CPU, memory, or custom and external metrics depending on the metrics pipeline. The HPA asks for more replicas when demand is above a target and fewer when it is below, subject to minimums, maximums, and configured scaling behavior. The scheduler still has to place those new pods.
If the cluster lacks capacity, replicas can remain pending and the application does not gain the expected throughput.
That is why node capacity is a separate loop. A cluster autoscaling capability, often provider-specific or an add-on, can add or remove nodes based on pending pods and utilization rules. It works alongside the scheduler, not instead of it. New nodes take time to provision, join, receive required daemon sets, pull images, and become usable. A sudden burst may exhaust the current fleet before node scaling catches up. Plan baseline capacity, use sensible pod requests, keep rollout headroom, and set limits that match the real ability of downstream systems to absorb traffic.
Vertical sizing is yet another concern.
Vertical tuning mechanisms can recommend or adjust resource requests, but changes may involve a restart and therefore need compatibility with availability goals. Scaling on CPU can work for some workloads, while queue depth, request rate, concurrent connections, latency, or a business backlog may better represent demand for others. An autoscaler that reacts to a noisy or delayed metric can oscillate. A front-end that scales perfectly may overwhelm a database that does not. Design the whole capacity chain: entry point, application, queue, cache, database, external API, and node fleet. Kubernetes gives you powerful loops. Good architecture gives them stable signals, safe bounds, and a system they can scale without moving the bottleneck somewhere else.
Kubernetes observability spans more than application logs.
Metrics tell you about rates, errors, utilization, saturation, and capacity trends. Logs provide chronological detail from applications, nodes, controllers, and security systems.
Traces connect one request across services and show latency relationships. Kubernetes events surface recent object-level decisions such as scheduling failures, image pull errors, and probe failures. API audit logs record security-relevant activity through the control plane boundary. Each signal answers a different question: none is enough alone. The Kubernetes project describes metrics, logs, and traces as the three pillars of observability. Cluster components expose metrics, commonly collected by a monitoring pipeline. Containers usually write application logs to standard output in error. The runtime and kubelet make them available locally, but production designs forward them through a node-level agent or another defined pipeline to storage independent of the node and pod lifecycle. Tracing requires application instrumentation and context propagation, then a collector in backend. Kubernetes itself does not provide one built-in long-term logging or tracing store. For the checkout service, build a correlation model. A user request gets a trace identifier at the edge. The gateway, checkout API, inventory service, payment adapter, and database client carry it where appropriate. Metrics report request rate, error rate, duration, queue depth, CPU, memory, and saturation. Logs include stable identifiers such as workload, namespace, version, request context, and error class without leaking sensitive values. Control plane and audit signals show if a rollout, policy denial, endpoint change, or node problem happened at the same time. Good observability makes failures explainable. It does not mean collecting every possible field forever. Set retention, access controls, redaction, sampling, costs, alert thresholds, and ownership deliberately. The goal is enough evidence to answer what changed, where the request slowed, which dependency failed, and whether the platform made the expected decision. When an application request fails, resist the urge to start with a familiar command. Trace the architecture in the direction the request travels. Is the external edge receiving the request? Did routing choose the expected service? Does the service have ready endpoints? Are the endpoints the intended pods? Is the pod ready, and is its container healthy? Can that container reach the required internal and external dependencies? If the pod is absent or not ready, move backward through its owning workload, scheduler status, node conditions, volume status, image pulls, policy decisions, and configuration inputs. This order prevents two common mistakes. The first is treating the first visible error as the cause. A gateway timeout may be caused by a service with 0 endpoints, but those endpoints may be absent because readiness checks are failing, and those checks may fail because a configuration change removed a dependency URL. The second is fighting a controller. Manually replacing a pod may temporarily alter a symptom while the deployment, replica set, or admission policy continues to recreate the broken state. Find the desired object and its conditions. Classify incidents by plane. Management plane failures include a bad change, missing approval, or configuration drift. Control plane failures include API availability, policy rejection, scheduler constraints, or failed reconciliation. Node plane failures include runtime, image, volume, CNI, disk, and resource pressure issues. Data plane failures include DNS, service route, network policy, TLS, application behavior, and dependency latency. Use this classification in runbooks and alerts.
It creates an escalation path that matches ownership. During recovery, make changes reversible, record timestamps, preserve evidence, and test the customer visible path after every remediation. Kubernetes gives you structured status and a consistent object model.
Use them to turn incident response from guesswork into a controlled traversal of the system. Namespaces provide a logical scope for many Kubernetes objects.
They are useful for organizing environments, teams, applications, and ownership. They also form the scope for many RBAC bindings, resource quotas, limit ranges, and policies.
But a namespace name alone is not a complete security or isolation boundary.
A secure multi-tenant design layers namespace scope with identity controls, API authorization, admission policies, network segmentation, resource limits, secret scoping, observability access, and sometimes separate nodes, clusters, or accounts for workloads with incompatible trust requirements.
Resource quota and limit range help make shared capacity more predictable.
A quota can constrain aggregate resource consumption or object counts in a namespace. A limit range can establish defaults or constraints for pod and container resources. These controls help prevent one team from consuming everything accidentally, but they need a humane operating model, documented requests, observable usage, approved exception paths, and platform support when a real capacity increase is justified. Quotas should turn hidden contention into a clear conversation, not a surprise production failure with no owner. For a platform serving several teams, define the tenancy model before the first cluster grows.
Who can create namespaces? Who manages RBAC and policies? Which add-ons run centrally? Who may install custom resources or admission webhooks? How do you separate development, staging, and production? Which workloads require dedicated nodes or a separate cluster? How are cost, audit access, log retention, and incident responsibility assigned?
The answer may range from a single trusted internal platform to strong isolation across separate clusters. Kubernetes provides primitives, but the trust model is your architecture. Make it explicit, review it when new capabilities are introduced, and avoid assuming a label or folder like namespace name has done all the security work.
Let's run the entire story once.
A team approves a new checkout service version.
Their delivery identity submits a deployment update to the API server. Authentication identifies the caller. RBAC authorizes the scoped action. Admission validates platform rules.
The API stores the desired template.
The deployment controller notices the new generation and creates a new replica set.
The replica set creates pods. The scheduler filters and scores nodes using resource requests, topology, taints, affinity, storage, and policy constraints. It binds each pod to a feasible node.
Kubelets prepare images, volumes, networking, and containers. Startup and readiness probes determine when each replica may become an endpoint.
Now a customer sends a request.
DNS directs it to the public edge.
The gateway or existing ingress implementation applies its listener and route configuration, then directs traffic to the checkout service. The service data plane selects a ready endpoint from the current endpoint slices. The pod handles the request with its declared configuration and service identity, possibly calling another internal service through DNS, persisting state through a designed data path, and emitting logs, metrics, and traces. If demand rises, HPA may request more replicas. The scheduler and node capacity loop determine whether they can become real.
If a replica fails, the controller replaces it.
If a node fails, the platform detects it and workload controllers create replacements where capacity and design permit.
Finally, operations observe the result. Metrics show traffic and saturation. Traces show latency across services.
Logs explain a specific error.
Events and object status show a failed image pull, scheduling constraint, readiness condition, or policy decision.
Audit logs show who changed the desired state. Backup and recovery evidence proves data can be restored. That is end-to-end Kubernetes architecture, a connected set of control loops, boundaries, and evidence paths. When you understand the flow,
the many object names stop being trivia. They become a map for designing, operating, and defending a real distributed system.